The next speaker is Jasper Bussemaker from German Aerospace Center. Jasper researches systems architecture optimization and its generation with MBSE processes, and he developed methods and tools for defining and solving such optimization problems and for connecting to simulation models. So he's a PhD from Delft University of Technology, and we're excited to hear more what they are doing at DLR and Seaside.
Use the microphone, right? Yeah. Thanks, Joseph. So I think you can see me and the slides online as well. Oh, do we have a clicker? Right. And it's not the first slide, but it's a nice one as well, but it's like the fourth slide or something. Yeah, thanks. So I will share some of the activities we're doing in the OD4HERA project, the EU-funded project, where we're using SysML to connect systems engineering tools. But first, a little bit on where I worked. I work at the German Aerospace Center. We're the national research agency for aerospace topics, and also the space agency for Germany, located all throughout the country with many different institutes with different focus areas related to aerospace. And I'm working at the Institute of System Architectures in Aeronautics. So we deal with the system level aspects of aviation systems. We're in Hamburg mostly, a little bit in Munich as well, with about 100 employees working on aviation systems, as you see here, like what would the next generation of green aircraft look like, but also on design methods. So how do we actually design these things? So that's relevant, of course, for what we're discussing here tonight. Well, and if we're designing such aircraft, we can do that within the DLR. That looks something like this. There are many, many different disciplines that we integrate and connect to each other and have to make sure that all the engineers involved in there speak the same language and exchange data in the same way. And that works quite well. So we've started these developments, these efforts, this experience about 20 years ago with a data format called CPEX. It's a way to parameterize a complete aircraft design. That then looks something like this. We also have workflow execution platforms, so we can execute analysis simulation tools that take CPEX as an input, do their calculations, write the results back to CPEX, and then converge that in a multidisciplinary optimization loop. And so a lot of experience here, it's just for aircraft, so in the aviation domain. At the same time, we realized that we need to expand our horizon a little bit to also look at the more typical systems engineering tasks like requirements and architecture, and also maybe look at other types of systems. So we're working on that, developing the next generation of digital engineering platforms, mainly in the OD4HERA project, but also in some other efforts internally in the DLR. So here we try to connect many different authoring and systems engineering MBSE tools together in one digital thread. Before I show more about this project itself, I would like to show a little bit of what we want to try to achieve in the end, namely let's say the highest level of design automation that you can achieve over the full, we're talking about conceptual design phase, not the complete life cycle of the system. But that's called system architecture optimization or system architecture design space exploration. The idea is that we have an optimization algorithm, so numerical, let's say classical optimization algorithm, not an LLM. That's why I asked the question before. Generating architecture. So we have an architecture design space definition, and from there we can create architecture instances and also more specific ones with different design parameters per architecture, let's say. So once we have this, we also have on the MDO side, the multidisciplinary analysis side, all this experience that is just told before about how to design aircraft, for example. So we can run the analyses using all the different engineering disciplines involved and the specific engineering tools. And we want to connect these two worlds. So once I have an architecture that was automatically generated, I want to synchronize it to, for example, CPEX, but it could also be other data formats, and then automatically run my multidisciplinary analysis and get the performance out of there to do trade studies and design space exploration. So by doing this, we get the full architecture level or system level impact of new technologies that we want to try to integrate. Yeah, and that's very interesting, of course, for research organizations, but also in general for companies who want to see how new, maybe subsystem level components impact the design at the system level. Right, we're there. We did this in some small test cases, but we're not there yet at the full multidisciplinary analysis level, let's say. But we're working on it. That's what I mean. So in OD4ERA is EU-funded project in the clean aviation scheme with these countries involved. We're trying to set up what we call an open digital platform. So it means a platform where we can connect different tools to it to have this kind of digital thread in the digital engineering steps, let's say. And for that, we have a central ontology. And the project didn't start out as a SysML2 project, but we compared different data alternatives, modeling languages. And we did arrive at SysML2 because there's really not a way around it nowadays. And it seems to be ready for the future. It's a research project, so we can afford to be new, let's say, innovative. Right, so we're developing this central ontology, and the way we're doing that is by first, of course, discussing about what kind of stuff do we want to put in there, what kind of concepts do we want to represent. I mean, this is all quite standard MBSE digital engineering stuff, right? So we're not reinventing the wheel too much at least now. Then look at SysML2, what it can already do natively, and then also develop some relatively small layers of extension libraries on top of that, and then connect authoring tools there. So far, not so crazy. Maybe here it's interesting to mention that we also want to both look at commercial tools and research tools, but okay. What's here is interesting to highlight is that the top process is really this typical collaborative process where you need all your experts involved to discuss what should we put in the ontology and how should we represent it. So for this, we found the system says code process to work very, very well with, as also we saw in previous presentations, we're just using Git, so nothing special there either. And then C-side editor because it's free and nicely accessible to everyone, so everyone can be involved in the discussions. And in the end, we also want to publish the libraries that we're creating on CSAND. I was hoping it would have already be the case, but take some time to get all the partners on board in like a big research project. So that's technology stack we're using here. It works very well. And then for connecting the authoring tools, in principle, all of the project partners are free to do as how they can choose how they want to do it. But most of them arrived at Seaside Automator because most of our research tools, for example, they're written in Python already. So then having a nice library for parsing, Python library for parsing SysML2 files, this is the best that's out there. And I do want to note that we already started this in 2020. We already started this in 2024. So already back then, Seaside Automator was a good tool and helped us with doing what we wanted to do. So very impressive indeed. Right. And this is where I hope that the resolution is good enough. But this is an example of the ontology layer we created for the architecture design phase, for system architecture. It's mostly just standard SysML2, except that we added some stuff to also define design parameters, like different types of design variables, continuous or discrete, to declare certain attributes as outputs, like optimization objectives or constraints. This is the architecture design library soon on CSAND. I don't know what soon means, but let's see. And then the more interesting part is that we can then combine this into what we call the architecture design space. We have different parts and actions which we, in our interpretation, we map to components and functions, but we agree that, there's not an official denomination of this or something, this mapping, but in the way we use it, we do it like that. And then we can have, for example, multiple parts performing the same function, and that would then mean a choice. You have to choose one of the parts because you cannot have multiple parts doing the same function. And then we can derive architecture instances from that. where we then actually do this down selection. So some of the parts are not selected, and some of them are, and parameters are assigned values, etc. So that's an the example of how we could use this ontology. Then we connected it to a tool called Door. It's the internal DLR tool. I wrote my PhD thesis on this. It's a way to model the architecture design space. So yeah, the ontology comes from this way of working basically, right? You define your functions, your components, you link them to each other, you define your architectural choices, your metrics, your design variables. Then you can use that to generate your architecture instances, but most importantly, you can use it to specify your formal optimization problem and then link to optimization algorithms. So you can actually automatically find your Pareto front of optimal designs, optimal architectures. And what that looks like, I'll show now in a short demo. It starts with some requirements that we've generated with another tool of ours, all model-based, so nicely referencing to objects and having different parameters and semantic constraints in SysML2. And then we can connect it to system architecting. So we got here some requirements, referencing systems and functions, parameters with units and semantic constraints, thanks. Then we import this in Adore, and we see here the functions from the systems, and we can create components and link them to existing parts. Name is synchronized, for example. Here we declare that some of functions are fulfilled by the component, but the component also needs additional functions. And then this is synchronized back into the architecture design space. So here we see that being created. And then to the functions, we can associate quantities of interest that we can link to existing parameters. Behavior, let's say this inequality and the number, they're automatically synchronized. So there's no data duplication, it's really coming from the SysML2 model. And then we can continue modeling. We can define additional layers of components for fulfilling our functions. For example, for rejecting heat, choose vapor cycle system, sorry for naming there, or a ram air heat exchanger. And you see the color of the arrows change, so that means we now have an architectural choice. And we have a design space of size 2 architectures. In reality, this is much bigger, of course. That looks then like this in SysML2. We have our 2 parts that we created, linking to the same action or the function. Yeah, and we can continue modeling like this. We have additional functions that are being induced by the components. One thing I want to highlight here is that this way of modeling the design space, we're modeling it as a directed graph, not a tree. So we can actually also have different components pointing to the same function through a different path, let's say. Like in the end, both components here, they need ram air, and that's modeled like this. It was very powerful. We have an additional needs action link here to declare that if I choose a different part, a certain part that also needs additional actions to be included. And like this, we can model our architecture design space with full bidirectional synchronization to SysML2. Right, so we have our architecture choice here. We can manually create architecture to validate that the behavior is correct of the design space model. And like this, I've created an architecture instance where I select a ram air heat exchanger to reject heat. And then in SysML2, it looks like this. We now have an architecture, right, design space, where we indeed have the ram air heat exchanger, and we don't have the alternative, the vapor cycles. As a little demo of what we can do with this. Right. And I want to go to the next. Yeah. So to conclude, a little demo of our next generation engineering platform, what we're working on to connect everything by SysML2. I showed the specific use case of using Adore to model architecture design spaces. And then the ontology development we do with the free tools from SenseMetry basically and Git. And then the two connections are now mainly done with Seaside Automator. So thank you.